Now we want to talk about medium-sized stars. So these are going to have a mass of between zero point 0.4 up to 8 times the mass of our sun. So notice that our sun is a member of this class of objects. Our sun is going to have a mass of 1, so 1 falls between these two categories. So if it was less than 0.4 times the mass of the sun, all it's going to be able to do is convert hydrogen into helium. But our sun is going to have a different fate. So currently, our sun is going to be converting hydrogen into helium. So that's what it's doing. And then those nuclear explosions is what is providing the thermal gas pressure that is keeping gravity at bay. Okay, so let's draw a picture then of our sun. Okay, and then let's say that this is the core of our sun where the hydrogen is being turned into the helium. Okay, now this part out here, this would be like the radiative zone and the convective zone and the photosphere. So all of this part is a part of the sun that is not burning. So there's no nuclear explosions occurring in this part of the sun. So the only part of the sun where the hydrogen is being turned into helium is going to be in the core of the sun. Okay, now our sun is eventually going to start to run out of hydrogen. So then that means the nuclear explosions are going to die down and our sun's core is going to begin to collapse. Now, as it collapses, the pressure on the inside of the core is going to go up, and so is the temperature. And if the temperature can reach this magic number of 100 million Kelvin, then the heliums in the core are going to begin to smash together and undergo nuclear fusion, and they are going to start to turn into the element carbon. So helium will begin to be nuclearly fused into carbon in the core of the sun. Now, what's going to happen to this part out here, though? So this part out here is going to be feeling the heat from these increased nuclear explosions in the core. So this part, the outer part of the sun, is going to expand. So the core is going to contract, but this part's going to expand. And so it's going to expand greatly, but I can't show that to you on this board because the board is too small. So this thing is going to expand, and so we're going to call this thing now a red giant. So if you notice in the picture, the color of the initial object is yellow because it's going to be hotter. If we go back to the previous picture and we were talking about the red dwarf, they were the red ones. But these objects, like our sun, are going to be hotter. So they're going to start out being yellow, and then when they expand and turn into this red giant thing, they are going to become the color red because the amount of energy that they're giving off is going to decrease. It's spread out over a larger surface area, so the temperature is going to look cooler and it's going to be the color red when that happens. Okay, and so I give you some facts about the red giant, about the diameter. So when our sun becomes a red giant, the radius of this object could go all the way to the radius of the orbit of the Earth. So that means Mercury is going to be incinerated. Mercury would be inside of this object. Venus would be inside of this object. And so we don't know about Earth, whether Earth would be swallowed up by this object or whether we'd be outside of it. But no matter what, Earth would be unlivable at that point because the surface of the Earth would be molten, the atmosphere would be ripped away, the oceans would have all boiled away. So things are going to be pretty bad on Earth when this happens. So I give you the diameter and I also give you the density of this object. Now, our sun is eventually, though, going to start to run out of helium. Okay, so the helium is being turned into carbon, but eventually our sun is going to start to run out of helium, and so gravity starts to win again. As the nuclear explosions die down, the core is going to collapse, and the temperature is going to go up again, and it's going to get hotter than 100 million Kelvin. But this time it's going to need to get to 500 million Kelvin before we can get to our next one, which is going to be neon. So our sun is never going to do it. Our sun is just not big enough to be able to generate the forces necessary, the pressures necessary, the temperatures necessary in order to forge neon in its core. So what's going to happen to the sun if this happens? So eventually the core is going to shrink and it's going to become a white dwarf. So the object that's going to be left over after our sun collapses is going to be a white dwarf. And that white dwarf is going to be about the size of the Earth. And then that white dwarf is going to eventually cool down and turn into a black dwarf. Sound familiar? Yeah, it was the same thing that was happening with the very small stars and the small stars. And so the same thing is going to happen to ours. The only difference is what's going to happen to the red giant part. So this red giant part is going to be jettisoned into outer space as a planetary nebula. So if you look at it, it's from a two-dimensional, it kind of looks like a smoke ring. But in 3 dimensions, it's this sphere that is going to expand into outer space. And it can get up to a diameter of 1 light year. So it will really, really go into outer space before it finally dissipates and disappears. Now, what happens to all that gas? So if you recall, this part of our sun, or this part here, this part of our sun contains a lot of hydrogen and a lot of helium. It's not being used for anything. It's not being ignited. Well, this stuff here expands to this thing when it becomes the red giant, and then when it's jettisoned into outer space as a planetary nebula, all of that hydrogen and helium goes back into outer space, and then it can be used as a fuel for another nebula, and then it can turn back into another star in the future. Okay, pretty interesting, eh? Okay, so let's continue here. And now let's show you again the HR diagram, so that down here in this corner was where the red dwarfs were located at. They were the color red. Okay, and you can see that all that they can do is manufacture helium. Okay, but then in this part up here of the HR diagram, so now we're getting into stars like our sun. They are going to be able to make carbon, okay, and other elements. So now let's go back to here, and let's talk about what would happen if you had a star that was hotter than the sun. So if our sun was bigger, it would be hotter, and it would be able to make neon. Okay, but then eventually these stars, which are going to be bigger than our sun, are going to start to run out of carbon. Okay, and then the core is going to collapse, and as the core collapses, the temperature is going to go up, and if it can get hotter still, then the neon can be converted into oxygen in the core. So notice what's happening is we're manufacturing the elements in the periodic table of elements. We started off with hydrogen, which formed as a result of the Big Bang. And then also some helium formed as a result of the Big Bang. But in the cores of stars, we're manufacturing the elements up to silicon in the periodic table through these nuclear explosions and nuclear fusion. So on our HR diagram, you will notice that the stars that we've been talking about, so these were the small stars, are down here. Okay, then you've got your medium-sized stars, which are right here, and so that's going to include the sun. And so your elements, this one is only going to be able to manufacture helium. These stars up here are going to be able to manufacture carbon through silicon. Now you might be wondering, well, what happens if it's hotter still? Could we manufacture anything above silicon? Yes, we can. But that's not going to happen with these medium stars. So we'll talk about that in our next segment. Okay, so here's our temperatures. So in order to be able to convert hydrogen into helium, you need 10 million Kelvin. In order to be able to convert helium into carbon, you need to have a temperature of 100 million Kelvin in the core. And then to be able to convert carbon into neon, you need a temperature of 500 million Kelvin in the core. So these are the temperatures required in order to manufacture these various elements in the core of the star. And then also look at the amount of time spent fusing. Do you notice anything about that? So in this particular size star, this is going to be a big one. So this star in this chart here is bigger than our sun. And so it's going to spend 7 billion years converting hydrogen into helium. Our sun is going to spend about 10 billion years converting hydrogen into helium. And it's been doing it for about 5 billion years. So our sun has about another 5 billion years left to go, and then it's going to start to run out of hydrogen. But this hypothetical star is much bigger. And so it's going to be converting hydrogen into helium for 7 billion years. But then notice that when it starts to convert helium into carbon, it's only going to be able to do that for about 500 million years. And then when it starts converting its carbon into neon, it will only be able to do that for 600 years. Okay, that's because you get the most bang for your buck. It is the most efficient way of getting energy out of nuclear fusion when you're converting hydrogen into helium. So as you start to try to fuse these heavier and heavier elements, you just don't get as much energy out of the nuclear reactions. And so that means that the star is going to have to use its remaining fuel at a much faster rate in order to keep those nuclear explosions going and keeping gravity at bay. So that by the time a star is converting silicon into iron, it's only going to do it for 1 day before it evolves into something else. Now, and also I wanted to show you this. We talked about the PP chain. So the PP chain, the proton-proton chain, was how you take two hydrogens and you smash them together and eventually you end up with helium. These are other chains. You don't need to know them for any kind of an exam, but it shows how you can forge these other elements inside of a star by using other nuclear fusion chains. So I just thought that you might enjoy looking at that. Did you enjoy it? I hope you did. So let's take a break, and when we come back, we're going to talk about large stars, stars larger than our sun, and what's going to happen to them.